the future before the exam. So we'll start smoothly today. I will ask you a few questions on the Clicker app to make sure that you're following. If you have any questions about what we've done last week or in the previous weeks, I can also take them. Then I will finish the part on evaluation, and then we'll jump to probabilities, some heavy math. All right, so let's first move to the questions. So here is, well, so this is in the vector space model, right? When we take documents as bags of words, meaning that we care about the number of times terms appear in documents. We could use the term frequencies in the vectors, right? Build document vectors where the coordinates are the term frequencies, right? Remember, it's one coordinate per term. Then we would put the term frequency. Why is that not a good idea to just put the term frequency and that's it? Is it because ranked retrieval then comes down to Boolean retrieval, which we've been covering in the first weeks of the course, and the whole linear algebra is a useless overhead compared to plain intersections of postings lists? Or is it because some terms may be concentrated in just a few documents? Or is it because the most relevant documents have low term frequencies and we need inverted term frequency instead? Or who said that this is not a good idea? This is in fact an excellent idea. So remember, term frequency is what we denoted as ETH, and it has two parameters in the subscript, a term and a document, and it is the number of times that said term appears in said document. And I am pleased to see that the majority is correct. Indeed, do you remember what we add in addition to the term frequency? What do we multiply it with very often? The IDF, yes, the inverted document frequency, right? It's not the only way, right? TF-IDF is the standard way by default. If you don't have any ideas, then just put the TF-IDFs. But I also told you that there's many variations of this. I even gave you the restaurant menu, the smart notation, with all the variations that you can have. If you don't want the IDF, then you can do without it. Not necessarily a good idea, but you can. If you want to renormalize, you can. If you don't want to renormalize, then you also have that choice. If you are not happy with just the term frequency, you have all kinds of variations with the log of that, or you can fall back to Booleans, just 1 or 0 for the term frequency. So you have a whole menu, but the default is TF-IDF if you don't have any specific needs beyond that. All right? So indeed, the reason why we do multiply with the IDF in general is that that wouldn't account for how rare a term is. So it might be that some terms are only used in very specific documents, specialized documents, whereas other terms are very frequent. And the stop words, for example, would have a very high document frequency and thus a very low inverted document frequency. Okay, so this is good. And the third one is actually made up because there is no such thing as an inverted term frequency. That, not that I know, at least. It's inverted documents frequency. And in fact, the low term frequencies would make the documents less relevant rather than more relevant. So it's the opposites. And in fact, to be fair, the person who answered true to the last one could be considered to be partially correct if you're on the query side. Because remember that we have this choice on the query side and document side, the weights we put. And we saw that it's not necessary to have the IDF on both the query side and the document side when we do the scalar product. So it's typical to have the IDF on the document vectors. And in the query vector, we can just put the term frequencies, right? So You wouldn't be entirely wrong of saying that it's an excellent idea on the query side. Let's move on to another question that I have for you, maybe this one. Because we're speaking about term frequencies, so what is the term frequency of term A in document 3? 1, 2, 4, or 11? That should be an easy one, right? Okay. Do we aim at 100% for that one? Yes, 100%. Very good. So indeed, it's just this one right here, right, that you see here around my mouse. All right, so this is good. This is the one I should have asked first, but I'm just going to check that everybody gets it correctly. What's the term frequency of term A? Okay, that should be answered in just a few seconds, 100%, right? The term frequency of term A, 1, 4, 11, doesn't make sense. Oh, 11. Okay, no, it doesn't make sense. The term frequency is for a term in a document, right? If you just say for a term, then that's incomplete, right? You need to say for that, for what document. Term frequency takes 2 parameters, a term in a document. What would be the name for maybe what you had in mind when you answered 11? What would be the name for that? It's not called term frequency, that would be called the total number of times it appears in the collection. Anybody? It's called the collection frequency, right? So 11 would be the collection frequency of term A. Yeah? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Right? All right. So collection frequency depends just on the term. Document frequency depends just on the term. Term frequency depends on the term and the documents. All right, so we've got things right now. And what would be the inverted document frequency of term A? 0, 1, 3, or 4? Remember the definition of inverted document frequency? So the inverted document frequency of term A. Remember logarithm of n over the document frequency, n being the total number of documents. Zero or one? Let's compute it. Total number of documents? 4, yes. How many documents contain term A? 4 also. It's a stop word. A is actually a stop word. It's everywhere. So 4 divided by 4 is, yes, 1. And log of 1 is 0 in any basis, right? Otherwise, I would have told you which basis for the log to use, but in any basis, the log of 1 is 0. So indeed, the correct answer is 0 because that's a stop word. That's the lowest inverted document frequency you can have is for the stop words that are absolutely everywhere. All right, let's maybe this one if you want to answer this one. When do we most likely need machine learning? To rank the documents using the vector space model, to construct the standard inverted index optimally, to find optimal weights to score documents in zone queries, or to display the results to the users in a way they understand? That's something I briefly showed a couple of weeks ago. But even if you didn't attend a few weeks ago, just machine learning should give you the right keywords, right? When you use machine learning, exactly, you optimize weights. All right. So That's it. To rank the documents, we just use a heap, remember, because we want the top 10, return the top 10, so we use a heap structure. There is no machine learning in there, right? We just accumulate the scalar product by summing over all the terms for every document. So there's no ML at all in there. All right, very good. So that was a way to start smoothly. Now, do we have any questions? Anything that wasn't clear last week or previous weeks? I'm giving you maybe 1 or 2 minutes to react. Put the courage in your hands to ask a question in front of everybody, or type it in the chat if you prefer to type it in the chat. We realized during the pandemic actually that with the courses on Zoom, there were more questions because people were a bit less shy of writing questions in the chat that Georges here is going to read for you, because it can be more intimidating to speak in front of everybody. That's why we have the seminars, by the way. The seminars are here in order to make you speak in front of other people. All right. So no questions, lecture hall, no raise hands. Okay, and on Zoom? A translation in which language? Vous voulez que je fasse le cours en français? Oh yeah, that would be more difficult. I'm not fluent enough. All right, so no questions. So let me ask you differently. So raise your hand if at that point you're comfortable with the material and ready to move forward. Okay, the majority of you. All right. And if you have any questions, you can ask them even later. You can send us an email. You can put your question in the forum. You can also directly ask your TA or me. So that's absolutely fine. I do recommend that you read the textbook, right? We have a textbook that has pretty much everything I'm telling you in the lecture. And sometimes it can also be easier to just read it at your own pace or to rewatch the recordings at your own pace. Oh, it says a participant has enabled translation. Set your speaking language for this meeting. So I'm going to say that it's in English. I would be curious which language you are going to translate these to. So this is English. And who knows what language I'm actually speaking. Maybe AI is actually making my lips move with another language. Anyway, so let me continue where we were. I think we were close to here. You remember that I left you with the evaluation of precision and recall for ranked retrieval system. For example, the vector space models. So these are systems that return the top K queries, the top 10 queries. Then you can click on next, next, next to get the next 10 and so on. And so in order to evaluate precision and recall, we just keep clicking on next, and every time we evaluate the current precision and recall, and we get that curve. Remember that that last time, so more precisely, we would get a curve like this. Basically, whenever there's a negative, there's an irrelevant result returned, it goes down. Whenever we have a relevant result, it goes up and to the right. And then we do a bit of cosmetics because this isn't really nice. So we do this, right? We take these horizontal lines to smooth it out. And then what we do is we don't do it for every new result. We only do it for at the beginning, then the first 10%, then the first 20%, first 30%, and then at the end, 100% of what we want, right? And that we get, with that, we get 11 points. That's called the 11-point interpolated average precision, 0, 10, 20, all the way to 100. By the way, just quick question that I remember from my physics lectures back then. We were actually in electronics when we were using the oscilloscopes and all of these devices. Who thinks we can compute that in real time, these green lines? That we can figure it out as the results come in. Who thinks we cannot? I see raise hands. Indeed, we cannot. That would require knowing the future. right? So this is something that you do at the end. But when you are here, you cannot possibly know in advance that this is going to be the next peak, right? So this is something that you do at the end. That was just a fun fact that I remember from the physics courses. All right. And so I explained to you that an awesome search engine is going to keep its precision high even as you click next. So it keeps answering with relevant documents. Of course, that only is going to be the case until you're out of relevant documents because you've returned them all. Then we saw that this is an awful search engine. And this one can actually not even be salvaged in the way we saw last time to just flip the results, because when you have an engine where you click next, you can, in order to swap the results, you would have to click next until the end and then swap the results. So computationally, it's not very practical. So that actually would be an awful search engine, not very useful. Okay. And then there's variations of that. One variation that people have is that instead of looking at the curve as a whole, they just take one metric, which is the area below the curve, this here. So they compute the area, the total area, and that gives you what's called the average precision, because in fact, it's kind of an average over the recall, right? And of course, when you do that, that would give you the maximum possible value, because that's the maximum area possible, right? Because you have the entire rectangle, and that would give you an area of, checking you're following, the area here is 0, exactly. All right, so that's like taking the integral if you have real numbers, but since it's discrete here, that's just a sum that you see right here. It's a discrete sum. And then what people do is that they repeat with plenty of other queries. They just keep drawing the same curve with plenty of queries. And then they again take the mean of that across the queries. So you could call it the average precision or the mean precision, but that's not very nice. So they came up with mean average precision, right? Which is a way of saying you do an average twice. Write the first one over as you go through the results, and the second one across the queries, right? And even more precisely across the information needs that are behind the queries. So that is called the mean average precision map. We have this game in academia of coming up with acronyms that actually are real words, and that's an example of that. So map, mean average precision. And that's the formula. It's just averaging twice, right? All right. Then there is something else, again, with the idea of not looking at the whole curve, but of trying to find a single number. The area is a single number, but this is something else. It's called the R precision. The idea is actually simple. Imagine that you have a specific information need and a query, and you know that there are exactly K documents that are relevant to your information need. K, that's just a number. Maybe it's 42. And so you know that there's 42 documents that are relevant to you. And so what you're going to do is fetch the first 42 results of the query, the same number, right? 42 relevant documents. So you are going to look at the first 42 results. And then at that point, you estimate the precision and the recall after 42 results. Now, there is something actually fun that happens when you do that, when you look at exactly the same number of documents as the number of relevant documents. It turns out that the precision and the recall are the same when you do that, right? And that you can see visually, right? So that would be the K relevant documents. They are all here. Then you return K. Do you realize that when you compute the ratio vertically, which is the recall, and when you compute the ratio horizontally, which is the, what's that called? Precision, yes? So you get the same results, because every time you divide, in that case, 8, so the true positives, divided by K for both the precision and the recall. So it turns out the precision is the same as the recall when you do that. Who sees that? Right? All right. And so visually, so this is the R precision. That's an example of when you've reached the R precision, the number of false positives and false negatives are exactly the same. That's the R precision when you are there. So it's the single number that is the precision and the recall at the same time. All right. And visually on the curve, if you want to directly plot it with no effort, just draw y equals x and intersect it with the curve, the 11-point interpolation, for example, and you get the R precision, right? It's just the point at which the precision becomes equal to the recall. So far, so good, right? So that's a very nice interpretation here that you have. All right, so now if I hear some mathematicians here that might say, yes, wait. It might be more than one intersection generally because the curve is actually not that nice in general. So yes, absolutely. It could be that you have weird cases in which there's multiple intersections. But anyway, that's the idea. All right. Okay, so that is the R precision. But there is more. There is one more thing that people like to do, this time again with a curve. That is actually borrowed from electronics. I think it means receiver operating characteristics or something. Receiver operator characteristics. All right, so that's borrowed from, oh, sorry?
Receiver operating characteristic.
Receiver operating characteristics. Yes, exactly, so ROC. That's something you can see, I think, on your internet box. If you look at your internet box internally, you might even see that tells you something over the signal strength over the internet. But anyway, how does it work? Well, imagine that you are on the beach and you have your Bitcoin detector and you're trying to see if you can find some Bitcoins on the beach, and you have this detector, which is some device that you oh, I have one right here. So that is a Bitcoin detector, and it has a little knob to test how sensitive it is. And so maybe at the start you set that to the minimum, and then you just go and try to see if there are any lying around. And then you realize it's not beeping, doesn't give you any positive results, so you're a bit disappointed. But you remember you have a knob, so maybe you can turn the knob a little bit to make it a bit more sensitive. Then you continue, and then it starts beeping a little bit, but still not satisfying. And then you realize, what if I turn the knob to the maximum, right, and make it super sensitive? And then you guess what happens, right? It's beeping all the time, and it's also completely useless, right? But in fact, if you draw the curve of that, when you turn the knob to increase the sensitivity in order to make it beep a bit more easily, you are going to get a curve that is known as the ROC curve. And I lost my clicker. Where did I put it? Over there. Yes. So this is the curve you get, basically. So the idea is that you increase the sensitivity, meaning that you are going to increase the recall. And then when you go on the right, you are going to be controlling, to have an effect on the specificity. So remember specificity, what it is. So the recall is how good you are at returning relevant results, right? That's the number of true positives divided by relevant documents. The specificity is the same thing, but on the right. It's your ability to correctly identify non-relevant documents, right? So that would be the number of true negatives divided by the total number of non-relevant documents. But here we do one minus just to get the mirror of the curve. And so that basically means that when we have a very high recall, we don't have so many false negatives, because this is what recall is about, right? You measure, you have high recall if you don't have so many false negatives. Here you would have a lot of false negatives. If you have very low recall, it means there's a lot of documents you're incorrectly not returning, even though they're relevant. Here you would have, if you're here, very few false positives. That's basically where you have very high specificity. You're very good at not returning irrelevant documents, so few false positives. And here you have a lot of false positives. So if you put it all together, few false positives, few false negatives, this is where you want to be. Lots of false negatives, lots of false positives, this is where you do not want to be. So the curve that you have here in that example is good, because it starts with very few false positives, and then you manage to decrease the number of false negatives as recall increases. And then at some point, you really get into very few false negatives, high recall, but that has a cost. Now specificity is actually getting worse, right? So this is decreasing the specificity. So you see, this is what this curve does. It basically show you how you control the false positives and the false negatives with your knob, the little knob that you turn. And again, it's a compromise to make, right? By turning the knob, you're getting higher recall. You might find more Bitcoins, but at the cost of beeping for nothing, right? So you have also then more false positives. For whom is that clear? Right? So that is the ROC curve. So we love to be here, where the curve is as much as possible like this. We do not like to be here, but do we really not like to be here? That is basically the question I asked last time. Is it really that awful? What if I give you this device that is very good at detection? Well, actually not good at all. It's beeping exactly when there's nothing, and it's not beeping when there is something. So it only has true false positives and false negatives. Who is going to buy this from me? Everybody, right? You just need to find where it doesn't beep, and there you go, right? So this is the same trick as I said last time. So this, in fact, is not awful at all. This is just as good if you swap the results. What you don't want is this. This is awful. This is just a device that randomly beeps, and it just gives you no information, right? So that is a really awful search engine if it has this curve. All right. I just wanted to throw this out of nowhere, but without telling you, I'm just saying that for those who love machine learning, there's plenty of more cool stuff you can do with this. And you can come up with other metrics. This one is called the normalized discounted, there's an N missing, cumulative gain, NDCG. So there's plenty more things you can come up with, plenty more metrics you can come up with to study your system, right? It's a variation of the map. You might recognize the formula here of the mean average precision. It's a variation of that with different weights. All right, but anyway, that's the end of this lecture. So there's plenty of other metrics you can have. So here it was about the quality of the system, so false positive, false negatives. But you also have the speed of the index construction that might be relevant. How much time does it take to reconstruct the index? That might also have an impact on the staleness of your results if it's the internet. The speed of search, this you want to be fast. If you want your users to be happy, they should get an answer in reasonable time. For a search engine, it should be just a few milliseconds. Of course, if you consider an LLM like ChatGPT or Perplexity, then users can accept a bit longer time because of the high quality of what they're going to get after that, right? So if you're sitting in front of an LLM and it needs 5 seconds to get a full report on the lepidopters in South Switzerland, that's actually worth the 5 seconds rate, right? So it depends on your use case. But that's also a metric, the speed that it takes, the latency. Then you have the expressiveness of a query language. Historically, the Boolean querying was the way to go, but it was very tough to use because the problem with Boolean querying is that you write a query, you don't get a lot of results, then you modify it, and now you get a lot of results. And it's very difficult in Boolean querying to find just the sweet spot in the middle, which is why phrase search, as is known in the more modern search engines work better, and also the vector space model allows you to search with more natural words, right? Because the query is just a document. The size of a collection, of course, is relevant. If you index the entire internet or just a small library, also makes a difference. Anyway, that's the end of this lecture. Do we have any questions? None here on Zoom? All right. So here I would like to congratulate you because we are done with the bachelor's level part, or at least what is said in the textbook to be, this is what we teach at the bachelor's level in university. So this is the end. But you know that in order to push you a little bit, and in your 3rd year of bachelor, you are allowed to take master's courses, so you can be exposed a little bit to master's level content. And in the remainder of this course, I will expose you to master's level content. So I have 2 more parts, this week, next week, and the week after that, that are a bit more advanced. The first one is going to be probabilistic information retrieval. And then language models, not the large ones, the more the old one, the ones that look less cool than LLMs, but still it's very interesting to see what we've been doing before that. And then we will be done. So we'll have at the end of the semester a wrap-up lecture to just rehearse what we've seen. We'll have a big quiz with the TAs where you play against the TAs and we see if you survive longer than the TA team. And I think you want to announce maybe the mystery game that with the TA team, they have a surprise for you.
So next week, we have planned a small surprise / mystery game for you. So you will see something appearing on Moodle page I think it will be under last week's material, namely a mystery game. And the first 3 submissions that make, like the first 3 students who make a correct submission will have a small sweet prize.
Thank you very much. So you see all the hard work that the TA team is putting in the course. So I hope you'll enjoy this little game. So let me stop the recording here.